Welcome, traveler, to a quiet journey into the elegant heart of linear algebra, a realm of profound patterns and interconnected structures. Tonight, we will drift gently through the concepts that describe our world in its most fundamental dimensions, uncovering the subtle dance of vectors, the quiet conversation of matrices, and the transformative shifts that shape our understanding of space itself. As we embark upon this exploration, allow the gentle rhythm of these ideas to guide your thoughts towards a peaceful contemplation and eventually a deep and restorative sleep. Linear algebra, in its essence, is the language of change and relationships, a powerful lens through which we can perceive the underlying order of the universe. It is a discipline that, despite its abstract nature, profoundly influences everything from the flight of stars to the currents of rivers, from the vast datasets of human knowledge to the intricate workings of the very devices we use. We will begin our quiet voyage by exploring the foundational concept of vectors, these elemental arrows of magnitude and direction that point the way through every dimension imaginable. Chapter 1. Vectors in Rn. We begin our exploration with an introduction to vectors, the building blocks of this mathematical universe. Linear algebra is a tool used across many disciplines, from the social sciences and business to the vast fields of science and engineering. In the sciences, vectors are indispensable, describing concepts such as displacement, the change in position from one point to another, velocity, the speed and direction of movement, acceleration, the rate of change of velocity, and force, a push or pull, and many other important physical concepts. Informally, a vector is an object that possesses both magnitude, its size or extent, and direction, the orientation in space. For example, to imagine a boat moving on a calm river, its velocity, which includes both its speed and the precise direction it is heading, can be perfectly represented by a vector. In the language of mathematics, a vector is typically represented by a column of numbers, a quiet stack of values. Each number in this column tells us something about the vector's presence in a particular dimension. The set Rn, pronounced Rn, is defined as a collection of column vectors, each containing n entries, where each of these n entries is a real number. A vector itself, within this set Rn, is an element, a column of n real numbers. For instance, a vector could be represented as a column with two entries, say, 2 and 3, living in R2. Or perhaps a vector in R3, with entries -3, 1, and -5, extending into 3 dimensions. We could even conceive of a vector in R100, a column of 100 real numbers, each patiently waiting in its designated place. As we continue our gentle exploration, we find that while column notation is standard, sometimes it is convenient to express vectors in a horizontal or row notation. This row notation includes a special symbol, a superscript t, which stands for transpose, and clearly separates the components of the vectors with spaces. It's like gently laying down a column of numbers to see them spread out horizontally. This distinction between a column vector and its row notation is important for our purposes. Let us now consider the two faces of a vector, its algebraic representation and its geometric representation. A vector's algebraic representation is simply its column of numbers, a precise list of its components. For example, a vector in R2 could be represented algebraically as a column with 2 on top and 3 below. This is its numerical fingerprint. On the other hand, a vector's geometric representation is a directed line segment in Rn, an arrow in space, starting at one point and ending at another, showing both its length and its orientation. A fascinating aspect of vectors is that they are not localized. This means that if two vectors have the exact same magnitude and the exact same direction, regardless of where they start, they are considered to be equal. For simplicity, and often for convenience, we frequently choose the starting point of a vector to be the origin, the central 0 point of our coordinate system, and its terminal point then directly gives us its coordinates. For instance, if a point V has coordinates, say, 2, a -4, and 9, then the vector pointing from the origin to V is represented algebraically as a column with 2, -4, and 9, in R3. This n-tuple, this ordered list of n numbers, is the algebraic representation, the true identity of our vector. We are free to move a vector around in space, as long as we preserve its magnitude and direction. However, moving it will change both its initial and terminal points. We say that the terminal point associated with a vector, when its initial point is the origin, is simply the point associated with that vector. Now, let us consider the operations we can perform on these fundamental mathematical entities, vectors. First, the equality of vectors. We say that two vectors in Rn are equal if and only if their corresponding entries are equal for all components from 1 to n. This simply means that their columns of numbers must match perfectly, entry by entry. We denote this by writing one vector equals another vector. A vector equation, stating that two vectors are equal, is therefore equivalent to a system of n individual equations, one for each component. For example, if we have a vector with 1, 2, 3, and another with 1, 2, 4, they are not equal, because their third components, 3 and 4, are different. Next, we explore vector addition. When we add two vectors, we simply add their corresponding entries. For example, adding a vector with entries 2, 4, 6 to a vector with entries 3, -5, 7 results in a new vector with entries 5, -1, and 13. Geometrically, the sum of two vectors follows what is known as the parallelogram law. Imagine one vector, and then imagine the second vector beginning where the first one ends. The resulting sum is the vector from the starting point of the first to the terminal point of the second, forming two sides of a parallelogram. For instance, if a boat moves with a certain velocity, and a person on that boat walks with another velocity relative to the boat, an observer on the shore would see the person move with a combined velocity, which is simply the sum of the boat's velocity and the person's walking velocity. These rules of vector addition reveal several comforting properties, much like the properties of adding real numbers. First, vector addition is symmetric, or commutative, meaning the order in which we add two vectors does not change the result. Vector u plus vector v is the same as vector v plus vector u. Second, a vector addition is associative, meaning that when adding three or more vectors, the way we group them does not affect the final sum. U plus v plus w can be grouped as u plus v then plus w, or u plus the sum of v and w. Third, there exists a special zero vector, represented as a column of all zeros, in Rn. This zero vector has the property that when added to any other vector, it leaves that vector unchanged. It is the additive identity. Finally, for every vector, there exists an additive inverse, denoted by a negative sign before the vector. This additive inverse is defined as a vector where each component is the negative of the original component. For example, if a vector has entries 1, -4, 2, its additive inverse would be -1, 4, -2. The key property of the additive inverse is that when a vector is added to its inverse, the result is the zero vector. It has the effect of cancelling out the original vector. The additive inverse of a vector has the same magnitude, or length, as the original vector, but points in the exact opposite direction. From vector addition, we naturally move to vector subtraction. The subtraction of one vector from another is simply defined as adding the first vector to the additive inverse of the second vector. This is done component-wise, just like addition. For instance, subtracting a vector with entries 3, -5, 7 from a vector with entries 2, 4, 6 results in a new vector with entries -1, 9, -1. Geometrically, the subtraction of vectors can be visualized as forming the other diagonal of the parallelogram from the terminal point of the second vector to the terminal point of the first. For vectors in Rn, where n is greater than 1, we do not define a component-wise vector multiplication, as we did for addition and subtraction. Such an operation would generally be of little practical use in linear algebra. However, we do define different types of vector products, which we will discuss a little later in our journey. In the meantime, we introduce scalar multiplication, the process of multiplying a vector by a real number, or scalar. When a vector is multiplied by a scalar, each of its components is multiplied by that scalar. We say that the vector has been scaled by the scalar. For this reason, real numbers are often referred to as scalars in linear algebra. Consider the effects of scalar multiplication. If the scalar is greater than 0, the new vector points in the same direction as the original vector, but its length is multiplied by that scalar. If the scalar is less than 0, the new vector points in the opposite direction, and its length is multiplied by the absolute value of the scalar. The vector formed by multiplying by -1 is simply the additive inverse. It has the same length as the original vector, but points in the opposite direction. Scalar multiplication also comes with its own set of properties. First, multiplying a vector by the sum of two scalars is equivalent to adding the results of multiplying the vector by each scalar separately. Second, multiplying a vector by the product of two scalars is the same as multiplying the vector by the first scalar, and then multiplying the result by the second scalar. Third, multiplying the sum of two vectors by a scalar is equivalent to adding the results of multiplying each vector by that scalar separately. Fourth, multiplying any vector by the scalar 0 always results in the 0 vector. Finally, a cancellation law states that if the product of a scalar and a vector is the 0 vector, then either the scalar itself must be 0, or the vector itself must be the 0 vector. This property might sound familiar, as it mirrors a similar rule for real numbers, where if the product of two real numbers is 0, at least one of them must be 0. Now, let us consider a special set of vectors in Rn, known as the standard basis. In Rn, we define vector E sub I to be the vector whose ith component is 1, with all other components being 0. The set of these vectors, E sub 1, E sub 2, and so on, up to E sub n, is called the standard basis for Rn. For instance, in R3, the standard basis consists of three vectors. E sub 1 is 1, 0, 0. E sub 2 is 0, 1, 0, and E sub 3 is 0, 0, 1. If a vector is written as a column of numbers, say V sub 1, V sub 2, up to V sub n, these entries, V sub 1, V sub 2, etc., are called the components of the vector. These components tell us how much of each standard basis vector is needed to construct the given vector. Our exploration now turns to a slightly different yet equally fundamental realm, vectors in Cn. Here, each component of a vector is a complex number, rather than just a real number. Complex numbers introduce a new layer of mathematical depth, but reassuringly, the operations of equality, addition, subtraction, scalar multiplication, and the cancellation law are all defined in Cn, just as they are in Rn. The only difference is that we replace real numbers with complex numbers in our calculations. The standard basis vectors in Cn are defined in the same way as in Rn, each E sub I vector having 1 in its ith component and zeros elsewhere. For example, a vector in C2 could have components like 1 minus 2i and 7. Or in C3, it could have components like 1 plus I, 2 minus 3i, and negative for plus 5i. These complex vectors behave consistently with the rules we've already learned, allowing us to perform operations such as 3 times a complex vector minus 2 times another complex vector, evaluating the expression component by component, carefully handling the complex arithmetic. As we journey further, we encounter the dot product in Rn, a function that takes two vectors in Rn and returns a single real number. This operation reveals much about the relationship between vectors. Later, we will adapt this idea to vectors in Cn using a slightly different operation involving complex conjugates. The dot product of two vectors, say u and v, is defined by multiplying their corresponding entries, and then summing up all these products. For instance, the dot product of a vector with entries 2, 3, and another with 5, 7, would be 2 times 5 plus 3 times 7, which equals 10 plus 21, resulting in 31. For vectors in R3, like 3, -5, 2, and -4, 4, and -2, their dot product would be 3 times -4, plus -5 times 4, plus 2 times -2, resulting in -12, -20, -4, which sums to -36. The dot product possesses several important properties. First, it is symmetric, meaning the dot product of u and v is the same as the dot product of v and u. Second, it exhibits linearity, meaning the dot product of a sum of vectors with a third vector is the sum of the dot products of each individual vector with the third, and scalar multiples behave as expected, where a scalar can be factored out of the dot product. These two properties are collectively known as linearity. Third, and crucially, the dot product of a vector with itself is always greater than or equal to 0. It is 0 if and only if the vector itself is the 0 vector. This property is known as non-negativity. A primary and significant use of the dot product is in determining the length, or norm, or magnitude, of a vector in Rn. The length of a vector u, denoted by two vertical bars around u, is defined as the square root of the dot product of u with itself. For example, the length of a vector with entries 2, 4, would be the square root of 2 times 2 plus 4 times 4, which is the square root of 20, or 2 times the square root of 5. For a vector in R3, with entries 2, negative 3, 4, its length would be the square root of 2 times 2 plus negative 3 times negative 3 plus 4 times 4, which simplifies to the square root of 29. It's important to remember that when we take the square root in this context, we always refer to the positive square root. This also implies that every non-zero vector has a length greater than 0, and the 0 vector, as expected, has a length of 0. Another useful property relates the length of a scalar multiple of a vector to the absolute value of the scalar and the length of the original vector. The length of c times vector u is the absolute value of c times the length of vector u. This simply means scaling a vector by c scales its length by the absolute value of c. A vector with a length of 1 is given a special name, a unit vector. If a vector is not the 0 vector, we can transform it into a unit vector by scaling it with the reciprocal of its length. This process is called normalization. The resulting unit vector points in the same direction as the original vector, but its length is precisely 1. For instance, to normalize a vector with entries 2, negative 4 and negative 1, we would divide it by its length, the square root of 21. Beyond length, the dot product provides a way to determine the angle between two vectors. In R2, this relationship can be understood through the law of cosines, which relates the lengths of the sides of a triangle to the cosine of one of its angles. By connecting the law of cosines to the definition of the norm, we arrive at a fundamental formula: the dot product of two vectors u and v is equal to the product of their lengths multiplied by the cosine of the angle between them. This formula allows us to find the angle between vectors, expressed in radians, from 0 to pi. For this definition of the angle to be meaningful, we need to ensure that the value of the dot product divided by the product of the lengths always falls within the domain of the inverse cosine function, which is from -1 to 1. This crucial inequality, stating that the absolute value of the dot product of u and v is less than or equal to the product of their lengths, is known as the Cauchy-Schwarz inequality. We will accept its validity without proof for our current discussion. Now, with this understanding, we can determine the angle between vectors. For example, to find the angle between a vector with entries 1, 4, and another with entries -2, 3, in R2, we would calculate their dot product, and divide it by the product of their lengths, taking the inverse cosine of the result. The angle would be approximately 0.833 radians. An especially significant case arises when the dot product of two vectors is 0. We say that two vectors are orthogonal, or perpendicular, if their dot product is 0. This definition of orthogonality is perfectly consistent with our angle formula. If the dot product is 0, then the cosine of the angle between them must be 0, which means the angle is pi over 2 radians, or 90 degrees, demonstrating their perpendicularity. We also note that every vector in Rn is orthogonal to the 0 vector, as their dot product is always 0. Given a vector, there are often many ways to produce a non-trivial vector that is orthogonal to it. For instance, in R2, a vector orthogonal to A, B, is simply -b. A, as their dot product is 0. In R3, a vector orthogonal to A, B, C, could be -b. A, 0, also resulting in a 0 dot product. The remarkable thing is that if we find a vector orthogonal to two other vectors, say u and v, then any scalar multiple of that vector will also be orthogonal to u and v. This property means that the line through the origin containing this orthogonal vector remains fixed, regardless of how we scale the vector. Let us now delve into the concepts of projection, components, and perpendiculars. Imagine two vectors. U and v is in Rn, where v is not the 0 vector. The projection of U onto V, often denoted proj V of U, is defined as the scalar quantity of U dot V divided by the norm of V squared, all multiplied by vector V. This effectively gives us the part of vector U that lies in the direction of vector V. We also refer to this as the projection of U in the V direction. For example, to find the projection of a vector with entries for a -8 onto a vector with entry 7, 1, we calculate their dot product, 20, and divide it by the norm of the 7, 1 vector squared, which is 50. We then multiply this scalar fraction, 20 over 50, by the vector 7, 1, which simplifies to 2/5 of the vector 7, 1. A key observation here is that the magnitude, or length, of vector V does not fundamentally affect the projection, only its direction matters. We can also express the projection using the unit vector in the direction of V. This gives us the length of U times the cosine of theta, multiplied by the unit vector V. This interpretation helps us visualize the projection as precisely the part of vector U that aligns with the direction of V. Next, we define the component, or scalar component, of vector U along vector V. This is simply the length of U times the cosine of the angle between U and V. It can also be expressed as the dot product of U with the unit vector in the direction of V. If this scalar component is negative, it means the projection of U along V will point in the opposite direction of V, even though we still consider it along the V direction. Finally, we introduce the perpendicular of U onto V, denoted perp V of U. This is defined as vector U minus the projection of U onto V. Geometrically, this represents the part of vector U that is completely orthogonal to vector V. An important property here is that the projection of U onto V and the perpendicular of U onto V are always orthogonal to each other. This means their dot product will always be 0. This makes intuitive sense, as one part lies exactly along the direction of V, and the other part is exactly 90 degrees away from it. Our journey now takes us to a parallel universe of vectors, those in Cn, the n-dimensional space of complex numbers. To effectively work with lengths of vectors in this realm, we need to recall how magnitudes are calculated for complex numbers themselves. For a real number x, its magnitude, or absolute value, is simply the positive square root of x squared. For a complex number z, its magnitude, or modulus, is the positive square root of z times its complex conjugate z bar. This leads us to the standard inner product in Cn, which is a generalization of the dot product. For two vectors u and w in Cn, their standard inner product, denoted by angle brackets around u, w, is found by multiplying each component of u by the complex conjugate of the corresponding component of w, and then summing all these products. The crucial difference from the dot product in Rn is that we take the complex conjugate of the components from the second vector. For example, if u is 1 plus I, 1 plus 2i, and w is 2 plus I, 1 plus I, their inner product involves computing 1 plus I times the conjugate of 2 plus I, plus 1 plus 2i times the conjugate of 1 plus I. The complex conjugation ensures that the inner product behaves correctly with complex numbers. This standard inner product in Cn, like the dot product in Rn, possesses several key properties. First, it exhibits conjugate symmetry, meaning the inner product of u and w is the complex conjugate of the inner product of w and u. Second, it displays linearity in the first argument, meaning that the inner product of a sum of vectors with a third is the sum of the inner products, and a scalar can be factored out of the first vector. Third, the inner product of a vector with itself is always a real number greater than or equal to 0, and it is 0 if and only if the vector itself is the 0 vector. This non-negativity property is vital. Just as in Rn, we use this non-negativity property to calculate the length, or norm, or magnitude, of vectors in Cn. The length of a vector u in Cn is the square root of its standard inner product with itself. For instance, to determine the length of a vector with entries 2 minus I, a negative 3 plus 2i, and negative for minus 5i, we would compute its inner product with itself, which involves multiplying each component by its own complex conjugate and summing the results. This simplifies to the square root of 59. The properties of this length in Cn also mirror those in Rn. First, the length of a complex scalar c times vector u is the magnitude of the complex scalar c multiplied by the length of vector u. Second, the length of vector u is always greater than or equal to 0, and is 0 if and only if vector u is the 0 vector. Finally, we define orthogonality in Cn, mirroring the definition in Rn. Two vectors u and w in Cn are orthogonal if their standard inner product is 0. For example, to check if a vector with 1 plus I, 1 plus 2i, is orthogonal to a vector with 2 plus I, and negative 1 minus I, we compute their standard inner product. If it turns out to be 0, as it does in this case, then the vectors are indeed orthogonal. We now briefly touch upon fields. The sets of real numbers, R, and complex numbers, C, which we have used for vector components and scalars, are special mathematical structures called fields. Loosely speaking, a field is a set where we can perform the four basic arithmetic operations: addition, subtraction, multiplication, and division, with the usual properties. For example, the set of integers Z is not a field, because while 2 and 3 are integers, their quotient, 2/3, is not. Similarly, the set of positive real numbers R+ is not a field, because while 2 and 3 are positive, their difference, 2 minus 3, is -1, which is not a positive real number. It turns out that the ability to add, subtract, multiply, and divide are precisely the properties we need for our scalar operations in linear algebra. In much of our work, we often refer to a universal set as a field F, with the understanding that F will be either R or C. Most of the time, the specific choice of F will not matter. However, there are occasions when we need to be explicit about which field we are using. For instance, solving x squared equals -1 has no solutions in the field of real numbers, but two solutions, positive I and negative I, in the field of complex numbers. We extend the definition of the standard inner product to Fn, where it is still the sum of the products of corresponding components, with complex conjugation applied if F is the field of complex numbers, and simply the dot product if F is the field of real numbers. Our final vector product in this chapter is the cross product, uniquely defined for vectors in R3. Given two vectors u and v in R3, the cross product returns a new vector, also in R3, that is orthogonal, or perpendicular, to both u and v. The formula for the cross product of u, with components u1, u2, u3, and v, with components v1, v2, v3, yields a new vector, where the first component is u2v3 minus u3v2, the second component is the negative of u1v3 minus u3v1, and the third component is u1v2 minus u2v1. For example, taking the cross product of a vector with 2, a -3, 5, and another with -2, 1, 4, results in a new vector with -17, -18, -4. The cross product also has important properties. First, the resulting vector u cross v is orthogonal to both u and v, meaning its dot product with u is 0, and its dot product with v is 0. Second, it is skew-symmetric, meaning u cross v is equal to the negative of v cross u. Third, the magnitude, or length, of u cross v is equal to the product of the magnitudes of u and v multiplied by the sine of the angle between them. This magnitude has a beautiful geometric interpretation. It represents the area of the parallelogram formed by vectors u and v. To determine the direction of the cross product, we use a convention known as the right-hand rule. If you align the pointer finger of your right hand in the direction of vector u, and your middle finger in the direction of vector v, then your thumb will point in the direction of u cross v. If you were to consider v cross u instead, you would have to turn your hand upside down, which physically demonstrates the skew-symmetric property. A question naturally arises: why is the cross product only defined for R3? For two non-parallel vectors in R3, there is always exactly one line through the origin that is orthogonal to both vectors. The cross product allows us to compute one non-zero vector on this unique line. However, when the dimension n is not 3, this simplicity vanishes. In R2, the only vector orthogonal to two non-parallel vectors is the trivial 0 vector. In Rn with n greater than or equal to 4, there are many different lines through the origin that are orthogonal to two given vectors, making it difficult to choose a single unique direction for a cross product. This is why the cross product is a special tool for R3. Good night. Chapter 2. Span. Lines and planes. As we drift deeper into the elegant world of linear algebra, we now turn our attention to the concepts of span, lines, and planes. These ideas allow us to understand how vectors combine to form larger, more intricate structures. First, let us define a linear combination. Imagine a collection of scalars C1, C2, and so on, up to Ck, from a field F. And a collection of vectors V1, V2, and so on, up to Vk, from Rn. A linear combination of these vectors is any vector that can be expressed as C1 times V1, plus C2 times V2, and so on, up to Ck times Vk. This is like taking our fundamental building blocks, the vectors, and scaling and adding them together to create new vectors. For example, if we have two vectors in R3, say 2, 0, 5, and -1, 1, 3, then the vector 9, -5, -5 is a linear combination of these two, because it can be formed by 2 times the first vector minus 5 times the second vector. The idea of a linear combination leads us directly to the concept of span. Given a set of vectors V1, V2, and so on, up to Vk, in Rn, the span of this set is defined as the collection of all possible linear combinations of these vectors. It's like imagining all the points in space that you can reach by taking various steps in the directions of your given vectors, and scaling those steps as needed. The set of vectors itself is often referred to as a spanning set for the space they create, and we say that the space is spanned by those vectors. For instance, consider two vectors in C2. The span of these two vectors would be all vectors that can be formed by multiplying the first by a complex scalar C1, and the second by a complex scalar C2, and then adding them. Similarly, in R3, if we have 4 vectors, their span would be all vectors formed by taking a real scalar multiple of each, and summing them up. A crucial observation is that the 0 vector, a column of all zeros, is always a linear combination of any set of vectors, since you can always multiply each vector by the scalar 0 and sum them up. A common question is whether a particular vector is an element of the span of a given set of vectors. To determine this, we try to express the target vector as a linear combination of the spanning set. This translates into a system of linear equations. For example, to see if the vector -3, 9, 2 is in the span of 1, 2, 1, and 1, -1, 0, we would try to find scalars C1 and C2 such that C1 times the first vector plus C2 times the second equals the target vector. If such scalars exist, then the vector is in the span, as it is in this specific instance. However, sometimes a vector is not in the span. Consider asking if the vector 0, 1, 0 is in the span of 2, 0, 5, and -1, 0, 3. Any linear combination of these two vectors will always have 0 as its second component. Therefore, a vector like 0, 1, 0, which has 1 as its second component, cannot possibly be formed by these two vectors, and thus, it is not in their span. Now, let us apply these ideas to describe lines in Rn. We begin with lines in R2, often called the xy plane, and then generalize to higher dimensions. A common way to describe a line in R2 makes elegant use of vectors. We consider a line L passing through points, say, x1, y1, and x2, y2, or having a y-intercept at 0, b, with a slope m. The table of common line equations gives us several forms. In the initial forms, we input a value for x to get a value for y. But in the last form, we introduce a parameter, t. We input a particular value for t to obtain the x and y coordinates of a point on the line. This number t, which can be any real number, acts as a guide, tracing out all the points along the line as it varies. This leads to the definition of parametric equations of a line in R2. For fixed real numbers p and q, where q is not 0, the parametric equations of a line in R2 passing through the point x1. y1, with a slope of p over q, are given by x equals x1 plus tp, and y equals y1 plus tq, where t is any real number. Each value of t generates a different point on the line. For instance, t equals 0 gives the starting point. T equals 2 moves us 2 steps along the direction of the line. As t varies over all real numbers, it sweeps out all the points on the line. The general expression for a vector equation of a line L in R2 involves a non-zero direction vector d with entries p, q, and a starting point vector u with entries x1, y1. The vector equation then becomes L equals u plus t times d, where t is any real number. For any value of t, the expression u plus td produces a vector in R2 whose terminal point has coordinates x1 plus tp, y1 plus tq, and this point lies on the line L. Some important remarks here. Letting t be 0 means the vector u is on the line. The line always passes through the terminal point u, and other points are reached by adding scalar multiples of the direction vector d. We say that the direction vector d is parallel to the line, and it provides the direction of the line. Although the direction vector d is parallel to the line, its terminal point is not necessarily on the line unless d itself is a scalar multiple of u. Also, there are many different vector equations that can describe the very same line L. For example, if we have 2 points u and v on a line, we can define the direction vector as v minus u, and then write the line equation as u plus t times v minus u. We now extend our understanding to lines in Rn. The concept remains remarkably similar. Lines in Rn can be described using the same vector equations as in R2. The main difference is the implicit number of components in the vectors, which in turn affects the number of parametric equations. For example, to line through a point u in Rn, with direction vector d in Rn, is given by L equals u plus t times d, where t is any real number. We say two lines have the same direction if their direction vectors are scalar multiples of each other. The parametric equations for a line in Rn, passing through a vector u, with direction vector d, expand to n individual equations. L1 equals u1 plus t d1. L2 equals u2 plus t d2, and so on, up to Ln equals un plus t dn, where t is any real number. For instance, a line through the point for a -3, 5, in the direction of -2, 4, 1, would have parametric equations x equals for -2t, y equals -3 plus for t, and z equals 5 plus t. A special case arises when lines pass through the origin. In such a scenario, a line can be described as the span of a single non-zero vector d. If vector d is in Rn, and is not the zero vector, then its span, which is all scalar multiples of d, represents a line through the origin, with d as its direction vector. This means that if a line can be expressed as the span of one vector, it must pass through the origin. Next, our gentle exploration leads us to the vector equation of a plane in Rn. This concept builds upon our understanding of lines and spans. For a plane in Rn through the origin, we need two non-zero vectors, u and v, which are not scalar multiples of each other. If u is not a scalar multiple of v, then the span of u and v, which is the set of all possible linear combinations of u and v, forms a plane in Rn through the origin. Vectors u and v are referred to as the direction vectors of this plane. Some critical insights here. The plane contains the terminal points associated with u and v when both start at the origin. If a vector p lies on this plane, it can be expressed as a linear combination of the direction vectors. Any plane defined by the span of two vectors must pass through the origin. To actually form a plane, the two direction vectors must be non-zero, and one cannot be a scalar multiple of the other. If they are scalar multiples, or if one is 0, the span collapses to a line or even just the origin, not a plane. The vector equation of a plane in Rn through the origin is simply p equals su plus tv, where s and t are any real numbers. For example, a plane in R3 through the origin, with direction vectors 2, 4, 6, and -1, 2, and -3, would have the vector equation P equals S times 2, 4, 6, plus T times -1, 2, and -3. The points 2, 4, 6, and -1, 2, and -3 are directly on this plane. We can also define a plane that does not pass through the origin. For a plane P in Rn, it is defined by a starting point vector u and two non-zero direction vectors v and w, such that v is not a scalar multiple of w. The set of all vectors P, such that P equals u plus sv plus tw, where s and t are any real numbers, forms a plane in Rn through u, with v and w as its direction vectors. We say that v and w are parallel to the plane. Important remarks here. Setting s and t to 0 simply gives us the vector u, meaning the point associated with u is on the plane. The plane extends from u in the directions of v and w, by taking their linear combinations. The terminal points v and w are not necessarily on the plane, unless they are scalar multiples of u. Also, as with lines, there are many different vector equations that could describe the same plane. We can even uniquely define a plane using three non-collinear points, that is, 3 points that do not all lie on the same line. Let these points be u, q, and r, with associated vectors u vector, q vector, and r vector. We want the equation of the unique plane containing these 3 points. The vectors q vector minus u vector and r vector minus u vector are parallel to the plane, and are not scalar multiples of each other since the points are non-collinear. Thus, we can express the equation of the plane as P equals u vector plus s times q vector minus u vector, plus t times a vector minus u vector, where s and t are any real numbers. For instance, to find a vector equation of a plane in R that contains points u equals 2, -4, 6, -8. Q equals 1, 3, -2, -4, and R equals 9, 7, 5, 3, we would first determine two non-parallel direction vectors by calculating q vector minus u vector and r vector minus u vector. The resulting equation would then be u vector plus s times the first direction vector plus t times the second direction vector. Our final stop in this chapter brings us to the scalar equation of a plane in R3, a unique and powerful way to describe planes, but only in R3. This method utilizes the cross product. Given two non-zero vectors, u and v in R3, where u is not a scalar multiple of v, we know that their cross product, denoted n vector equals u cross v, is orthogonal to any plane to which both u and v are direction vectors. This n vector is referred to as a normal vector to the plane. Now, suppose p0 vector and p vector are 2 points on the plane. Then the vector p vector minus p0 vector, which lies on the plane, must be orthogonal to the normal vector n. This gives us the normal form of the plane. N vector dot p vector minus p0 vector equals 0. Expanding this normal form, we arrive at the scalar equation, or general form, of the plane. Ax plus by plus cz equals d, where a, b, and c are the components of the normal vector n, and d is the dot product of n vector and p0 vector. The components of the normal vector are simply the coefficients of x, y, and z in the scalar equation. This allows us to quickly identify a normal vector from any given scalar equation. Some important remarks about planes through the origin. A plane passes through the origin if and only if the zero vector satisfies its equation. This means the constant d in the scalar equation ax plus by plus cz equals d would be 0. Geometrically, this implies that both direction vectors u and v, when starting at the origin, must lie on the plane. It is important to emphasize that the terms scalar equation, normal vector, and normal form of a plane are not unique. Normal vectors of a plane are any non-zero vectors orthogonal to any vector parallel to the plane. If n is a normal vector, then Cn, for any non-zero scalar c, is also a normal vector. Thus, a plane does not have a unique normal vector or normal form. Similarly, multiplying a scalar equation by a non-zero scalar does not change its solution set, so a plane does not have a unique scalar equation. Good night. Chapter 3. Systems of linear equations. As our quiet journey continues, we now enter the realm of systems of linear equations, a landscape where multiple relationships between variables intertwine. We begin with introductory examples that illustrate how these systems naturally arise. Imagine a market scenario: 3 watermelons and 7 kiwis cost $19, while 2 watermelons and 5 kiwis cost $13. Our task is to determine the individual cost of a watermelon and a kiwi. We introduce variables W for the price of a watermelon and K for the price of a kiwi. This translates into a system of two linear equations: 3W plus 7K equals 19, and 2W plus 5K equals 13. To solve this, we seek values for W and K that satisfy both equations simultaneously. A crucial step involves combining these equations in a way that eliminates one variable. For instance, multiplying the first equation by 2, and the second by 3, then subtracting the results, eliminates W. This leaves us with an equation for K, and negative K equals negative 1, so K equals 1. Substituting K equals 1 back into the first equation reveals that W equals 4. Thus, a watermelon costs $4, and a kiwi costs $1. We can verify these values by plugging them into both original equations, confirming they both hold true. The core idea in solving such a system is to manipulate the equations to eliminate variables, thereby simplifying the problem. This process can be approached in various ways. Now, let us formally define the terms associated with these systems. A linear equation in n variables, or unknowns. x1, x2, and so on, up to xn, is an equation that can be written in the form a1 x1 plus a2 x2 plus and so on, up to an xn equals b. The scalars a1, a2, and so on, up to an, are the coefficients of their respective variables, and b is called the constant term. A system of linear equations is a collection of m linear equations in n variables, each equation following the linear form we just described. We use a convention where a sub ij refers to the coefficient of variable xj in the ith equation. We say that a set of scalars y1, y2, and so on up to yn solves a system of linear equations if, when we substitute these values for x1, x2, and so on up to xn, every equation in the system is satisfied. We also say that the vector y, formed by these scalars in a column, is a solution to the system. It's important to note that if even one equation in the system is not satisfied by the proposed values, then that vector is not a solution. For example, in the system x1 minus 2x2 plus 3x3 equals 1, 2x1 minus 4x2 plus 6x3 equals 2, and 3x1 minus x2 plus x3 equals 3, the vector 1, 0, 0 is a solution, because when substituted, all three equations hold true. However, the vector negative 2, 0, 1 is not a solution, even though it satisfies the first two equations, it fails the third. The set of all solutions to a system of linear equations is called the solution set. The nature of these solution sets is profoundly important. A linear system can exhibit one of three distinct outcomes for its solution set. 1. It can be empty, meaning there are no solutions that satisfy all equations simultaneously. 2. It can contain exactly one element, a unique solution. Or 3. It can contain an infinite number of elements, an infinite number of solutions, described by one or more parameters. For instance, the simple equation 2x equals 4 has a unique solution, x equals 2. However, the equation 2x plus 4y equals 6 has an infinite number of solutions. We can express x in terms of a parameter t, such as x equals 3 minus 2t, where y equals t, and t can be any real number. This parameter t allows us to generate every possible solution. A system like 2x plus 3y equals 4 and 2x plus 3y equals 5 presents an empty solution set, as the left-hand sides are identical but the right-hand sides differ, making it impossible to satisfy both simultaneously. When a system's solution set is empty, we call it inconsistent. If it has a unique solution or infinitely many solutions, we call it consistent. When solving systems, it's not always immediately obvious which of these three outcomes will prevail. The key strategy is to manipulate the original system into an equivalent system that is easier to solve. Two linear systems are considered equivalent if they possess the exact same solution set. Our goal is to perform manipulations that preserve this equivalence. We use specific tools, called elementary operations, to transform systems of linear equations. Consider a system of m linear equations in n variables, labeled from E1 to Em. The following three operations are fundamental. 1. Equation swap, interchanging any two equations. Ei swapped with Ej. 2. Equation scale, multiplying any equation by a non-zero scalar c. Ei becomes c times Ei. 3. Equation addition, adding a multiple of one equation to another equation. Ej becomes Ej plus c times Ei, where I is not equal to j. These operations are sometimes referred to as type 1, type 2, and type 3 operations, respectively. The remarkable truth is that if a single elementary operation of any type is performed on a system of linear equations, the new system produced will always be equivalent to the original system, preserving its solution set. It's crucial to exercise caution. Multiplying an equation by 0 is not an elementary operation, as it can lead to a loss of information and an altered solution set. Similarly, adding an extra equation that introduces new restrictions can make a system non-equivalent. When manipulating a system, we must strive to neither lose nor add information. At any point, if we produce an equation of the form 0 equals a, where a is a non-zero number, then the system is inconsistent, and we stop immediately. We refer to the equation 0 equals 0 as the trivial equation. It is always true but contains no information. If we generate trivial equations, we typically move them to the end of the system by swapping. This ensures we maintain the original number of equations, even if some become trivial. Our ultimate goal is to reach a final equivalent system, one whose solution set is readily apparent. This final system is not unique, as different sequences of operations can lead to different but equivalent forms. The systematic process of solving a system of linear equations often involves two main phases. The first is the forward elimination phase. Here, we strategically use elementary operations to transform the system into a simpler form. We typically try to solve for variables in alphabetical or numerical order. We ensure the first equation contains the first variable with a non-zero coefficient, then use this equation to eliminate that variable from all subsequent equations. We repeat this process for the next available variable in the next equation, and so on, moving down through the system. Any trivial equations, like 0 equals 0, are moved to the end. This phase results in a system where variables are progressively eliminated, creating a triangular-like structure. Once forward elimination is complete, we can obtain the solution set through back substitution. Starting with the last non-trivial equation, we solve for its corresponding variable. Then, we substitute this value back into the preceding equations to solve for other variables, continuing this upward process until all variables are determined. This reveals any free variables, which can be assigned parameters, leading to an infinite number of solutions, or a unique solution if no free variables exist. Alternatively, instead of stopping at forward elimination and using back substitution, we can continue simplifying the system with a backward elimination phase. This extension yields an even simpler and unique final equivalent system. First, we scale each non-trivial equation so that its leading coefficient, the first non-zero entry, becomes 1. Then, starting from the last non-trivial equation, we use it to eliminate its corresponding variable from all equations above it. We move upwards, repeating this process for each leading variable, until each leading variable appears in only one equation, and its coefficient is 1. These additional steps, after forward elimination, are collectively known as backward elimination. When both phases are complete, we reach a reduced row echelon form, a state of maximal simplicity and uniqueness for the system. The process of manipulating equations can become cumbersome, especially with many variables. This is where matrices provide a powerful and elegant alternative. When solving systems, we observe that the variables themselves are often rewritten many times, but their importance is primarily at the beginning and end of the process. In the intermediate steps, only the coefficients and constant terms are truly necessary. This leads us to the definition of matrices. An M by n matrix, denoted A, is a rectangular array of scalars with m rows and n columns. Each scalar within the matrix is called an entry, and its position is denoted by a sub-ij, where I indicates the row number and j indicates the column number. For a system of linear equations, the coefficient matrix A is simply the matrix formed by all the coefficients of the variables. The entry A sub ij is the coefficient of variable xj in the ith equation. To fully represent the system, we use an augmented matrix, denoted by a vertical bar B. This matrix combines the coefficient matrix A with an additional column containing the constant terms from the right-hand side of the equations. This column is represented by vector B. Just as we performed elementary operations on equations, we can perform elementary row operations, or arrows, on the augmented matrix. These arrows directly correspond to the elementary operations on equations. Row swap, interchanging two rows. Ri swapped with a j. Row scale, multiplying a row by a non-zero scalar c. Ri becomes c times Ri. Row addition, adding a multiple of one row to another row. Rj becomes a j plus c times Ri, where I is not equal to j. These matrix arrows are also sometimes referred to as type 1, type 2, and type 3 operations. A row that contains all zero entries is called a zero row. If a matrix B is obtained from a matrix A by a finite number of arrows, we say that B is row equivalent to A. At any point in this process, we can pause and immediately write down the system of linear equations that corresponds to the current augmented matrix. The first column corresponds to x1, the second to x2, and so on, up to the second to last column for xn. The last column represents the constant terms. Since arrows maintain equivalence, the system of equations corresponding to the modified augmented matrix is always equivalent to the original system. The forward elimination phase using arrows transforms the augmented matrix into a row echelon form, or REF. A matrix is in row echelon form if 1. All zero rows are grouped at the bottom. 2. The leading entry, the leftmost non-zero entry in any non-zero row, appears in a column to the right of the leading entries of all rows above it. The leading entries in an REF matrix are called pivots, and their positions are pivot positions. Columns containing pivots are pivot columns, and rows containing pivots are pivot rows. Each pivot column and pivot row will contain exactly one pivot. For example, a matrix with pivots in the 1, 1, 2, 3, and 3, for entries is in REF. However, if a leading entry is not to the right of the leading entry in the row above it, the matrix is not in REF. The backward elimination phase, or the Gauss-Jordan algorithm, transforms the REF matrix into a reduced row echelon form, or RREF. A matrix is in reduced row echelon form if 1. It is in REF. 2. All its pivots are leading ones, meaning they are equal to 1. 3. The only non-zero entry in a pivot column is the pivot itself, all other entries above and below the pivot must be 0. The RREF of a given matrix is unique. This uniqueness allows us to denote it as RREF of A. This entire process, from an arbitrary matrix to its RREF, is known as the Gauss-Jordan algorithm. The RREF of the augmented matrix provides a clear roadmap to the solution set. A system is inconsistent if, at any point, we obtain a row in the augmented matrix that looks like 0, 0, 0, 1, where the last entry is a non-zero number. This corresponds to the equation 0 equals 1, which is impossible. For a consistent system, we categorize variables based on pivot positions in the REF of the coefficient matrix. If the jth column contains a pivot, xj is a basic variable. Otherwise, xj is a free variable. Free variables can be assigned parameters, allowing us to express basic variables in terms of these parameters. The rank of a matrix A, denoted rank of A, is the number of pivots in its RREF. The rank provides critical information about the system's consistency and the nature of its solution set. The system rank theorem states that a system of linear equations with coefficient matrix A and augmented matrix A vertical bar B is consistent if and only if the rank of A is equal to the rank of a vertical bar B. If the ranks are different, the system is inconsistent. If a system is consistent, the number of parameters in its solution set is given by n minus the rank of A, where n is the number of variables. This difference, n minus rank of A, is also called the nullity of A. So, nullity of A tells us how many free variables, or parameters, are needed to describe the solution set. Now, let us consider special types of linear systems. A system of linear equations is homogeneous if all the constant terms on the right-hand side of the equations are zero. Otherwise, it is non-homogeneous. A homogeneous system always has at least one solution, where all variables are zero. This is called the trivial solution. This also means homogeneous systems are always consistent. The set of all solutions to a homogeneous system with coefficient matrix A is called the null space of A, denoted null of A. The null space is always a subspace, a concept we will explore further. A remarkable property of homogeneous systems is that if U and V are solutions, and C is a scalar, then U plus V is also a solution, and C times U is also a solution. This means the solution set is closed under addition and scalar multiplication. For non-homogeneous systems, if the system is consistent, its solution set can be expressed in a particular way. Let xp be a particular solution to the non-homogeneous system Ax equals b. Then the entire solution set is the sum of xp and every vector in the null space of A. In other words, the solution set to a consistent non-homogeneous system is a translation of its associated homogeneous system's solution set, shifted by a particular solution. Geometrically, this means parallel lines or parallel planes. Good night. Chapter 4. Matrices. As we continue our serene exploration, we now focus on matrices, powerful mathematical objects that extend beyond simply holding coefficients. In the previous chapter, we saw how matrices concisely represent systems of linear equations. Here, we delve deeper into their intrinsic properties and operations. First, let's revisit the column space of a matrix. For an m by n matrix A, its column space, denoted col A, is defined as the span of its columns. Recall that the span is the set of all possible linear combinations of those columns. This means the column space is a subspace of Rm. The system of linear equations Ax equals b is consistent if and only if vector b belongs to the column space of A. This connection is profound, revealing that whether a system has a solution depends entirely on whether the right-hand side vector can be formed by combining the matrix's columns. Next, we introduce the transpose of a matrix. For an m by n matrix A, its transpose, denoted a superscript T, is an n by m matrix where the entry in the ith row and jth column of a transpose is the entry in the jth row and ith column of A. In simpler terms, a transpose is formed by making all the rows of A into the columns of a transpose, in the same order. This is the motivation behind our row notation for vectors, essentially treating them as transposes of column vectors. For example, if A is a 2 by 3 matrix, its transpose will be a 3 by 2 matrix. Just as we defined the column space, we now define the row space of a matrix. For an m by n matrix A, its row space, denoted row A, is the span of its transposed rows. So, we take each row of A, treat it as a vector, transpose it into a column vector, and then find the span of these new column vectors. A key insight here is that the transposed rows of A are precisely the columns of a transpose. This means that row A is equivalent to the column space of a transpose. A very useful property is that applying elementary row operations to a matrix does not change its row space. Now, let's consider matrix equality. Two matrices A and B are equal if and only if two conditions are met. First, they must have the same size, the same number of rows and columns. Second, their corresponding entries must be equal.
A sub ij must equal b sub ij for all rows I and columns j. We denote this simply by writing A equals B.
This entry-by-entry comparison might seem exhaustive, but there's an elegant shortcut. Two matrices of the same size are equal if and only if they produce the same result when multiplied by any vector. This property connects matrix equality to their transformative action. A crucial lemma here is column extraction. Multiplying a matrix A by the ith standard basis vector E sub I yields precisely the ith column of A. With this understanding, we arrive at matrix multiplication. For an M by N matrix A and an N by P matrix B, their product AB is an M by P matrix. The JTH column of the product AB is obtained by multiplying matrix A by the JTH column of matrix B. This means each column of AB is a linear combination of the columns of A. When calculating the product AB, it's essential that the number of columns in the first matrix A equals the number of rows in the second matrix B. If these numbers don't match, the product is undefined. Matrix multiplication is generally not commutative, meaning AB is usually not equal to BA, even when both products are defined. The order truly matters. We can also calculate the entries of the product matrix AB one by one. The entry in the ith row and jth column of AB is the dot product of the ith row of A with the jth column of B. Matrices also support arithmetic operations beyond multiplication. Matrix addition. For two M by N matrices A and B, their sum. A plus B is another M by N matrix, where each entry is the sum of the corresponding entries of A and B. This operation is only defined for matrices of the same size. Matrix addition shares familiar properties. It is commutative. A plus B equals B plus A. It is associative. The grouping of sums does not change the result. There exists an additive inverse for every matrix. For a matrix A, its additive inverse, negative A, is a matrix where each entry is the negative of the corresponding entry in A. When a matrix is added to its additive inverse, the result is the zero matrix. The zero matrix, denoted by a large O, is an M by N matrix where all entries are zero. It acts as the additive identity, meaning A plus O equals A. It's important to distinguish the zero matrix from the scalar zero and the zero vector. Scalar multiplication of a matrix. For a scalar C and an M by N matrix A, the product CA is an M by N matrix where each entry is C times the corresponding entry in A. This scales the entire matrix. Scalar multiplication also has properties mirroring real number arithmetic. C times the sum of A and B is CA plus CB. The sum of scalars C and D times A is CA plus DA. C times D times A is the same as C times the quantity DA. And the special case of negative 1 times A is simply the additive inverse of A. We also explore properties of the matrix transpose with respect to these operations. The transpose of a plus B is a transpose plus B transpose. The transpose of CA is C times A transpose. And critically, the transpose of a product AB is B transpose times A transpose. Notice the reversed order. This is a common point of attention. Finally, the transpose of A transpose is simply A itself. Now, we focus on square matrices, those with an equal number of rows and columns. N by N matrices. Within square matrices, we encounter special structures. An upper triangular matrix is a square matrix where all entries below the main diagonal are zero. The main diagonal consists of entries AII from the top left to the bottom right. A lower triangular matrix is a square matrix where all entries above the main diagonal are zero. The transpose of an upper triangular matrix is a lower triangular matrix, and vice versa. Also, the product of two upper triangular matrices is upper triangular, and similarly for lower triangular matrices. A diagonal matrix is a square matrix where all entries not on the main diagonal are 0. It's often denoted diag A11, A22, and so on, up to ANN, using only its diagonal entries. All diagonal matrices are both upper triangular and lower triangular matrices. The most simple example of a diagonal matrix is the n by n0 matrix. Another crucial example is the identity matrix, denoted I, or I sub n for an n by n matrix. This is a diagonal matrix where all diagonal entries are 1. The identity matrix acts as a multiplicative identity, meaning A times IN equals A, and IM times A equals A, for appropriate sizes. For vectors in Rn, IN times vector x equals vector x. If the identity matrix is multiplied by a scalar C, the result is a diagonal matrix where all diagonal entries are C. Next, elementary matrices. A matrix obtained by performing a single elementary row operation on an identity matrix is called an elementary matrix. These matrices are powerful because pre-multiplying any matrix A by an elementary matrix E performs the same row operation on A. This means performing a sequence of arrows on a matrix A to produce a matrix B is equivalent to multiplying A by a sequence of elementary matrices. EK, EK-1, and so on, up to E1, where B equals EK times E1 times A. The order of multiplication of elementary matrices is critical. Finally, the matrix inverse. For an n by n matrix A, we ask if there exists another n by n matrix B, such that B times A equals the identity matrix, or A times B equals the identity matrix. If such matrices B and C exist, they are called a left inverse and a right inverse, respectively. For square matrices, a profound result states that if both a left and right inverse exist, they must be equal. And even more powerfully, for square matrices, a left inverse exists if and only if a right inverse exists. This leads to the definition of an invertible matrix. An n by n matrix A is invertible if there exists an n by n matrix B, such that AB equals BA equals the identity matrix IN. This unique matrix B is called the inverse of A, denoted A inverse. The invertibility of a matrix is a cornerstone of linear algebra. The invertibility criteria state that for a square matrix A, the following are equivalent. A is invertible. The rank of A is n. The RREF of A is the identity matrix IN. This gives us a powerful algorithm for checking invertibility and finding the inverse. We construct a super-augmented matrix, a vertical bar IN, and then find its RREF. If the RREF is IN vertical bar B, then A is invertible, and B is A inverse. If the RREF of A is not IN, then A is not invertible. The determinant, which we will discuss next, also provides an elegant criterion for invertibility. Good night. Chapter 5. Linear transformations. As our quiet journey continues, we now explore linear transformations, these elegant functions that reshape vector spaces while preserving their fundamental structure. Up to this point, matrices have served as arrays of numbers, storing critical information for systems of linear equations. But their role extends far beyond this. Matrices can define functions. A function determined by a matrix A, an m by n matrix, is a function T sub A, that maps vectors from Rn to Rm. This function is defined by matrix vector multiplication. T sub A of vector x equals A times vector x. For example, if A is a 3 by 2 matrix, T sub A takes an input vector from R2, multiplies it by A, and outputs a vector in R3. This means T sub A takes two-dimensional vectors as input and produces three-dimensional vectors as output. The functions determined by matrices possess very special features. Matrix vector multiplication is linear, meaning it distributes over vector addition. A times U plus V equals a U plus a V, and it allows scalar multiples to be factored out. A times CU equals C times AU. These properties are so important that we give a name to any function that exhibits them, a linear transformation. A function t, mapping vectors from Rn to Rm, is a linear transformation, or linear mapping, if it satisfies two properties. 1. Linearity over addition. T of u plus v equals T of u plus T of v. 2. Linearity over scalar multiplication. T of cu equals C times T of u. In this context, Rn is the domain, the set of input vectors, and Rm is the codomain, the set of possible output vectors. A fundamental example of a linear transformation is precisely the function determined by a matrix. The linearity of these functions is inherent in the linearity of matrix vector multiplication. From now on, T sub A will refer to the linear transformation determined by A. A useful alternate characterization of a linear transformation exists: a function t is linear if and only if, for any two vectors u and v, and any scalar c. T of cu plus v equals c times T of u plus T of v. This single condition elegantly combines both linearity properties. Linear transformations also have a profound relationship with the zero vector. A linear transformation T always maps the zero vector of its domain to the zero vector of its codomain. T of zero vector equals zero vector. If a function does not map 0 to 0, it cannot be linear. When checking if a function is linear, we first ensure that it maps the zero vector to the zero vector. Then, we look for any non-linear terms in its definition. Terms like x squared, or x times y, or x1 times x2 times x3, are non-linear. If such terms are present, the function is likely not linear, and a counterexample can definitively prove it. If the function maps 0 to 0, and appears to contain only linear terms, then we proceed to prove its linearity using the definition. Next, we explore the range of a linear transformation, and the concept of onto's transformations. For a linear transformation T, mapping from Rn to Rm, its range, denoted range T, is the set of all possible output vectors. T of x, for all vectors x in Rn. The range of T is always a subset of Rm. Since a linear transformation always maps the zero vector to the zero vector is always in the range of T, meaning the range is never empty. A powerful proposition connects the range of a linear transformation T sub A to the column space of its defining matrix A. The range of T sub A is precisely the column space of A. This means that the system of linear equations Ax equals b is consistent if and only if vector b is in the range of T sub A. A linear transformation T is said to be onto, or surjective, if its range is equal to its entire codomain. Rm. The onto criteria states that for a linear transformation T sub A, defined by matrix A, the following are equivalent. T sub A is onto. The column space of A is equal to Rm. The rank of A is equal to m, the number of rows in A. This means that T sub A is onto if and only if its associated matrix A has a rank equal to its number of rows. If the rank is less than m, the range of T sub A will be a smaller subspace, like a plane in R3, and therefore not onto R3. Now, we consider the kernel of a linear transformation and one-to-one transformations. The kernel of a linear transformation T, mapping from Rn to Rm, denoted ker T, is the set of all input vectors x in Rn, whose output is the zero vector in Rm. T of x equals the zero vector. The kernel of T is always a subspace of Rn. Since T of the zero vector always equals the zero vector is always in the kernel, meaning the kernel is never empty. A proposition states that the kernel of T sub A, the linear transformation determined by matrix A, is precisely the null space of A. Recall that the null space is the solution set of the homogeneous system Ax equals the zero vector. A linear transformation T is said to be one-to-one, or injective, if whenever T of u equals T of v, then u must equal v. In simpler terms, distinct input vectors always map to distinct output vectors. The one-to-one criteria states that for a linear transformation T sub A, defined by matrix A, the following are equivalent. T sub A is one-to-one. The null space of A contains only the zero vector. Null A equals the set containing only the zero vector. The nullity of A is 0. The rank of A is n, the number of columns in A. This means T sub A is 1 to 1 if and only if its associated matrix A has a rank equal to its number of columns. If the rank is less than n, then there will be non-trivial solutions to Ax equals the 0 vector, meaning multiple input vectors map to the 0 vector, and thus T sub A is not 1 to 1. Combining the onto criteria and the 1 to 1 criteria, we arrive at a powerful result concerning square matrices. For a square matrix A, the following statements are equivalent. A is invertible. T sub A is invertible. T sub A is 1 to 1. T sub A is onto. The null space of A contains only the 0 vector. The column space of A is Rn. The nullity of A is 0. The rank of A is n. The RREF of A is the identity matrix In. This comprehensive set of equivalent conditions highlights the deep interconnectedness of concepts in linear algebra. A remarkable truth emerges: every linear transformation is determined by a matrix. In a previous section, we saw that any matrix defines a linear transformation. Now, we complete the circle: every linear transformation T, mapping from Rn to Rm, can be expressed in the form T of x equals A times x for some unique matrix A. This matrix A, which depends on T, is called the standard matrix of T, denoted T in square brackets with epsilon. The columns of this standard matrix are formed by applying the transformation T to each of the standard basis vectors. E1, E2, and so on, up to En, and then arranging these transformed vectors as columns in the matrix. This construction is remarkably simple. We only need to know what the transformation does to these n fundamental basis vectors to determine its action on any other vector in Rn. This matrix representation provides an elegant and compact way to express the linear transformation. A special case applies to linear transformations from R to R. Any such linear transformation T of x is simply C times x for some real number C. This means linear functions through the origin are fully characterized by a single scalar factor. By combining our understanding of functions determined by matrices and the standard matrix of a linear transformation, we see a seamless connection. The standard matrix of T sub A is A itself, and the matrix that determines T is the standard matrix of T. This means the two processes are inverse to each other. Now, let us consider special linear transformations: projection, perpendicular, rotation, and reflection, and see how their standard matrices beautifully capture their geometric actions. Consider the projection transformation proj W of U, which projects a vector U onto a line through the origin in R2, in the direction of a non-zero vector W. We can prove that this projection transformation is linear, because of the linearity properties of the dot product and scalar multiplication. The standard matrix of this projection has a specific form: its columns are the projections of the standard basis vectors onto W. Geometrically, all images of this projection lie on the line spanned by W, meaning its range is that line, not the entire R2. Thus, it is not an onto transformation. Also, many different vectors can project to the same image on the line, meaning it is not a one-to-one transformation. Its kernel will contain more than just the zero vector. Next, consider the perpendicular transformation perp W of U, which yields the part of vector U that is perpendicular to a non-zero vector W. We can prove that this transformation is also linear, since it is defined as U minus proj W of U, and both U and proj W of U are linear. The standard matrix of the perpendicular transformation is also derived by applying the transformation to the standard basis vectors. Now, let's ascend to R3. Consider the projection onto a plane through the origin. We can define this using the plane's normal vector, n, which is orthogonal to the plane. Any vector U projected onto the plane is simply U minus its projection onto the normal vector n, that is, perp n of U. Since perp n is a linear transformation, this projection onto a plane is also a linear transformation. The standard matrix of this projection onto a plane is formed by projecting each standard basis vector onto the plane. Geometrically, all images of this projection lie within the plane itself, so its range is the plane, not the entire R3. Thus, it is not onto. And many different vectors project to the same point on the plane, meaning it is not one-to-one. Our next special transformation is rotation about the origin by an angle theta, counterclockwise in R2, denoted R sub theta. We can prove this is a linear transformation by showing that it can be written as a matrix vector product. Using polar coordinates and trigonometric angle sum identities, we find that the standard matrix of R sub theta is given by cosine theta, negative sine theta, cosine theta. Geometrically, any vector in R2 can be obtained by a rotation from an appropriate starting vector, so its range is R2, meaning it is an onto transformation. Also, rotating distinct vectors always results in distinct images, so it is a one-to-one transformation. Finally, reflection about a line through the origin in R2, denoted ref W. This transformation reflects any vector u across the line spanned by a non-zero vector w. The reflection of u across the line is given by u minus 2 times the perpendicular of u onto w. We can show that this reflection transformation is linear, due to the linearity of the perpendicular transformation. The standard matrix of this reflection, its columns formed by reflecting the standard basis vectors, has a specific form involving the components of W. Geometrically, like rotation, reflection maps R2 onto R2, so it is an onto transformation. And distinct vectors reflect to distinct images, so it is a one-to-one transformation. Our next step in this mathematical journey is to understand the composition of linear transformations and how it relates to matrix multiplication. If T1 is a linear transformation from Rn to Rm, and T2 is a linear transformation from Rm to Rp, then their composition. T2 circle T1 is a function that first applies T1, and then applies T2 to the result. This composite function maps from Rn to Rp. A key proposition states that the composition of two linear transformations is itself a linear transformation. This follows directly from the linearity properties of T1 and T2. Even more profoundly, the standard matrix of the composite linear transformation T2 circle T1 is equal to the product of the standard matrices of T2 and T1, in that order. Matrix multiplication, which might have seemed abstract, now has a clear geometric meaning. It represents the sequential application of linear transformations. This result provides a very efficient way to find the matrix representation of a composite transformation. A special case of composition arises when a linear transformation T maps from Rn to Rn, in which case we can apply T multiple times. The pth power of T, denoted T to the power of P, is defined inductively as T applied P times, with T to the power of 0 defined as the identity transformation. The standard matrix of T to the power of P is simply the pth power of the standard matrix of T. This makes computing repeated transformations very elegant. Good night. Chapter 6. The Determinant. As we continue our gentle journey into the heart of linear algebra, we now encounter the determinant, the single number that holds profound insights into the behavior of a square matrix. Recall that for a 1-by-1 matrix A, consisting of a single entry, say A11, it is invertible if and only if A11 is not 0. Its inverse is simply 1 over A11. For a 2-by-2 matrix A, with entries A11, a 1-2, a 2-1, a 2-2, it is invertible if and only if A11 times A22 minus A12 times A21 is not 0. This special number, A11 A22 minus A12 A21, determines invertibility for 2-by-2 matrices. We give this number a name, the determinant. Formally, for a 1-by-1 matrix A, its determinant, denoted DETA, is simply its single entry A11. For a 2-by-2 matrix A, its determinant, DETA, is A11 A22 minus A12 A21. For example, the determinant of the matrix 6, 8, and negative 3, 2, is 6 times 2 minus 8 times negative 3, which equals 12 plus 24, or 36. We now generalize this definition to n-by-n matrices. To do this, we first need the concept of a submatrix. For an n-by-n matrix A, the ijth submatrix, denoted M sub ij of A, is the n-1 by n-1 matrix obtained by removing the ith row and jth column from A. The determinant of this submatrix DETM sub ij of A is known as the ijth minor of A. The determinant of an n by n matrix A, where n is greater than or equal to 2, is defined recursively. It is the sum of A1j times -1 to the power of 1 plus j times the determinant of the 1jth submatrix of A. This is called the expansion along the first row of the determinant. It means we multiply each entry in the first row by a signed minor, alternating plus and minus signs, and sum them up. This recursive nature means that for a 3 by 3 matrix, we'll evaluate 3 2 by 2 determinants, and for a 4 by 4 matrix, for 3 by 3 determinants, and so on. A remarkable feature of the determinant is that it may be evaluated by expanding along a ny row, not just the first. The ith row expansion of the determinant uses each entry aij multiplied by -1 to the power of I plus j times the determinant of its corresponding submatrix mij of A. This also applies to columns. The jth column expansion uses each entry aij multiplied by -1 to the power of I plus j times the determinant of its corresponding submatrix mij of A. In practice, it is often easiest to choose a row or column that contains many zeros, as this will significantly reduce the number of submatrix determinants needing computation. Some determinants are particularly easy to compute. If a matrix A has a row consisting only of zeros, then DETA equals 0. If A has a column consisting only of zeros, then DETA equals 0. If A is an upper triangular matrix, or a lower triangular matrix, then its determinant is simply the product of its diagonal entries. A 1 1 times a 2 2 times, and so on, up to a n n. This implies that the determinant of the n by n identity matrix In is 1. Also, the determinant of A is equal to the determinant of A transpose. Now, we move to computing the determinant in practice using elementary row operations. We can systematically simplify a matrix A by performing arrows, transforming it into a matrix B, whose determinant is much easier to compute. Since arrows have a predictable effect on the determinant, we can relate DETA to DETB. The effect of arrows on the determinant is as follows. Row swap: if B is obtained from A by interchanging two rows, then DETB equals -DETA. Row scale: if B is obtained from A by multiplying a row by a non-zero scalar C, then DETB equals C times DETA. Row addition: if B is obtained from A by adding a non-zero multiple of one row to another row, then DETB equals DETA. These rules also hold true if we replace row with column. However, it is a crucial warning not to use column operations when performing other matrix calculations, as they disrupt many properties of a matrix. Using these rules, we can obtain the determinant of an arbitrary matrix. For example, to find the determinant of a 3 by 3 matrix, we can perform row operations to transform it into an upper triangular matrix, keeping track of any row swaps or row scales. Each row addition leaves the determinant unchanged, each row swap multiplies the determinant by -1, and each row scale multiplies the determinant by the scalar used. By tracking these changes, we can work backwards from the easily computed determinant of the triangular matrix to find the determinant of the original matrix. The determinant's most fundamental property connects it directly to invertibility. A square matrix A is invertible if and only if its determinant is not 0. This theorem is a cornerstone of linear algebra. If A is invertible, its RREF is the identity matrix, whose determinant is 1. By tracking the effect of arrows on the determinant, we find that if A is invertible, DETA must be non-zero. Conversely, if A is not invertible, its RREF must contain a row of zeros, meaning its determinant is 0. This connection is vital. A non-zero determinant means the matrix can be inverted, while a zero determinant means it cannot. Another essential property is the determinant of a product. For two n by n matrices A and B, the determinant of their product AB is equal to the product of their individual determinants, DETA times DETB. This property simplifies many calculations. It is important to note that generally, the determinant of a sum A plus B is not equal to the sum of their determinants. A powerful corollary states that AB is invertible if and only if BA is invertible. This is because invertibility depends on a non-zero determinant, and DET-AB equals DET-BA. Another useful corollary: for an invertible matrix A, the determinant of A inverse is 1 divided by the determinant of A. We can even find an explicit expression for A inverse. Recall that for a 2 by 2 matrix A, if its determinant A D minus BC is not 0, its inverse is 1 over the determinant, times a new matrix with entries D, negative B, negative C. A. This general idea extends to n by n matrices. For an n by n matrix A, the ijth cofactor of A, denoted Cij of A, is negative 1 to the power of I plus j, times the determinant of the ijth submatrix of A. The adjugate of A, R denoted adjective A, is an n by n matrix whose ijth entry is the jith cofactor of A. That is, the adjugate is the transpose of the matrix of cofactors. A key result, which we state without proof, is that A times adjective A equals adjective A times A, which equals DETA times the identity matrix IN. From this, if DETA is not 0, we can derive the formula for the inverse. A inverse equals 1 over DETA times adjective A. While this method is general, it's often computationally intensive for large matrices. In practice, using the Gauss-Jordan algorithm to find the inverse is usually more efficient. Finally, Cramer's rule. This rule provides a method for solving systems of n linear equations in n unknowns by using determinants. If Ax equals b is a system of equations and dETA is not 0, then the jth component of the solution vector xj is given by dETA divided by dETA, where Aj is the matrix formed by replacing the jth column of A with the column vector b. Cramer's rule is particularly useful if we are only interested in a single component of the solution, as calculating many determinants can be slow for large systems. Our final journey in this chapter leads us to the determinant and its geometric interpretation. In R2, the determinant has a beautiful connection to the area of parallelograms. For two vectors u and v in R2, the absolute value of the determinant of the matrix formed by placing u and v as columns represents the area of the parallelogram with sides u and v. For example, the area of the parallelogram with sides 2, 5, and 4, 1 is the absolute value of the determinant of the matrix 2, 5, 4, 1, which is negative 18, so the area is 18 square units. The absolute value is important as area is a non-negative quantity. This extends to higher dimensions. The absolute value of the determinant of an n by n real matrix can be interpreted as the scaling factor of volumes in Rn. If the determinant is 0, the volume scales to 0, intuitively aligning with a non-invertible matrix, as such a scaling cannot be reversed. Good night. Chapter 7. Eigenvalues and Diagonalization. As our quiet journey into linear algebra continues, we now approach the fascinating landscape of eigenvalues and diagonalization, concepts that reveal the intrinsic behavior of linear transformations. First, what is an eigenpair? For an n by n matrix A, which represents a linear transformation T sub A, we consider its effect on a vector x. T sub A of x equals A times x. Typically, when a vector x is multiplied by A, both its length and its direction change. However, there are special vectors, for which the direction remains unchanged, or is simply reversed. These exceptions are particularly interesting and form the focus of this chapter. Imagine a vector x, when multiplied by A, results in a new vector that is simply a scalar multiple of the original vector x. Ax equals lambda x, where lambda is a scalar. This means the new vector points in the same or opposite direction as x, it has only been scaled. For instance, if A is a 2 by 2 matrix with 1, 3, 3, 1, and x is 1, 1, then Ax is 4, A4, which is 4 times x. The vector x has been scaled by a factor of 4, but its direction remains identical. If x is 1, negative 1, then Ax is negative 2, 2, which is negative 2 times x. Here, x has been scaled by -2, meaning its direction is reversed. We now formalize these ideas. For an n by n matrix A, a non-zero vector x is an eigenvector of A if there exists a scalar lambda such that Ax equals lambda x. The scalar lambda is then called an eigenvalue of A, and the pair lambda, x is an eigenpair of A. It's crucial that an eigenvector is non-zero, as the zero vector always satisfies a times zero vector equals lambda times zero vector for any lambda, which would be trivial. Our next step is to find these special eigenvalues and their corresponding eigenvectors. We call Ax equals lambda x, or a minus lambda I times x equals the zero vector, the eigenvalue equation, or the eigenvalue problem. Here, I is the n by n identity matrix. We seek non-trivial solutions for x, non-zero eigenvectors. This is possible if and only if the matrix A minus lambda I is not invertible, which means its determinant must be 0. The expression det A minus lambda I is called the characteristic polynomial of A, denoted C sub A of lambda. The equation C sub A of lambda equals 0 is the characteristic equation of A. The eigenvalues of A are precisely the roots of this characteristic polynomial. For an n by n matrix, its characteristic polynomial is always a polynomial of degree n in lambda. For example, to find the eigenvalues of a 2 by 2 matrix 1, 2, 2, 1 over the real numbers, we form the matrix A minus lambda I, which is 1 minus lambda, 2, 2, 1 minus lambda. Its determinant is the characteristic polynomial, which is lambda squared minus 2 lambda minus 3. Setting this to 0 gives us the characteristic equation, lambda squared minus 2 lambda minus 3 equals 0. This factors into lambda minus 3 times lambda plus 1 equals 0. The roots, lambda 1 equals 3, and lambda 2 equals -1, are the eigenvalues of this matrix over R. Sometimes, the characteristic polynomial has no real roots. For instance, the matrix 0, 1, -1, 0 has a characteristic polynomial of lambda squared plus 1. Setting this to 0, lambda squared plus 1 equals 0 has no real roots. This means this matrix has no real eigenvalues. Geometrically, this matrix represents a 90-degree clockwise rotation. Since such a transformation always changes a vector's direction, it makes sense that it has no real eigenvectors. However, over the complex numbers, this matrix does have eigenvalues, lambda 1 equals I and lambda 2 equals -I. The characteristic polynomial possesses general features. For an n by n matrix A, with characteristic polynomial C sub A of lambda equals Cn lambda to the power of n plus Cn minus 1 lambda to the power of n minus 1, and so on, up to C1 lambda plus C0. The coefficient Cn is always -1 to the power of n. The coefficient Cn minus 1 is -1 to the power of n minus 1, times the trace of A, where the trace is the sum of the diagonal entries of A. The constant term C0 is simply the determinant of A. These features provide useful red flags to quickly check if our characteristic polynomial calculations are on the right track. The fundamental theorem of algebra guarantees that any degree n polynomial has n complex roots, counting multiplicities. Therefore, an n by n matrix always has n complex eigenvalues. There is a direct connection between these eigenvalues and the trace and determinant of A. The sum of all n eigenvalues, including repetitions, is equal to the trace of A. The product of all n eigenvalues, including repetitions, is equal to the determinant of A. These properties further confirm the consistency of our calculations and deepen our understanding of matrix properties. Once we have found an eigenvalue lambda of a matrix A, we can then find its corresponding eigenvectors. We do this by solving the eigenvalue equation. A minus lambda I times x equals the 0 vector. This is a homogeneous system of linear equations, and the non-zero solutions x are the eigenvectors associated with that eigenvalue lambda. For each eigenvalue, we examine this system and find its solution set. The general solution for x will define all possible eigenvectors for that lambda. These non-zero solutions form the set of eigenvectors. Note that if x is an eigenvector for lambda, then any non-zero scalar multiple of x is also an eigenvector for lambda. This means that eigenvectors are not unique, but rather form a direction. This concept of direction leads us to eigenspaces. For an n by n matrix A and an eigenvalue lambda, the eigenspace of A associated with lambda, denoted E sub lambda of A, is the solution set to the homogeneous system A minus lambda I times x equals the zero vector. In other words, E sub lambda of A is precisely the null space of A minus lambda I. Important remarks about eigenspaces. The zero vector is always in E sub lambda of A. However, by definition, the zero vector is not an eigenvector. So the eigenspace consists of all eigenvectors plus the zero vector. Lambda is an eigenvalue for A if and only if its eigenspace E sub lambda of A is not just the zero vector. E sub 0 of A, the eigenspace for eigenvalue 0, is simply the null space of A. A crucial result states that eigenvectors corresponding to distinct eigenvalues are linearly independent. If a matrix A has k distinct eigenvalues, lambda 1, lambda 2, and so on, up to lambda k, and we select one eigenvector for each of these distinct eigenvalues, then that set of k eigenvectors is linearly independent. This property is vital for diagonalization. Now, we arrive at diagonalization. In certain applications, such as computing high powers of a square matrix A, efficiently, directly multiplying A by itself many times is computationally intensive. Diagonalization offers an elegant solution. If A is similar to a diagonal matrix D, meaning A equals PDP inverse, for some invertible matrix P, then A to the power of k is simply PD to the power of kp inverse. Since D is a diagonal matrix, computing D to the power of k is trivial, we just raise each diagonal entry to the power of k. This allows us to compute A to the power of k much more simply. PD to the power of kp inverse. This relationship means that A to the power of k is also diagonalizable. This leads to the definition of similar matrices. Two n by n matrices A and B are similar over a field F, if there exists an invertible matrix P, such that A equals PBP inverse. Similar matrices share many important properties. They have the same characteristic polynomial, and thus, the same eigenvalues. They also have the same determinant and the same trace. A matrix A is diagonalizable over a field F, if it is similar to a diagonal matrix D over F. This means there exists an invertible matrix P such that P inverse AP equals D. Matrix P is said to diagonalize A. A key proposition states that if A is diagonalizable, then its characteristic polynomial has n roots, possibly with repetition, in F. Moreover, the diagonal entries of the diagonal matrix D are precisely the eigenvalues of A. The converse to this is not always true. A matrix can have n eigenvalues in F, but not be diagonalizable. However, if A has n distinct eigenvalues in F, then it is diagonalizable over F. The eigenvector basis criterion for diagonalizability states that a linear operator T is diagonalizable over F if and only if there exists an ordered basis of Fn consisting entirely of eigenvectors of T. This directly extends to matrices. A matrix A is diagonalizable over F if and only if there exists a basis of Fn consisting of eigenvectors of A. This means that to diagonalize A, we need to find n linearly independent eigenvectors. The matrix P that diagonalizes A will have these eigenvectors as its columns. The resulting diagonal matrix D will have the eigenvalues on its diagonal, in the order corresponding to the eigenvectors in P. We also introduce algebraic multiplicity and geometric multiplicity. For an eigenvalue lambda of matrix A, its algebraic multiplicity, denoted am lambda, is the number of times the term lambda minus lambda appears as a factor in the characteristic polynomial. Its geometric multiplicity, denoted gm lambda, is the dimension of the eigenspace E sub lambda of A. The geometric multiplicity tells us the maximum number of linearly independent eigenvectors associated with that eigenvalue. A crucial proposition connects these two multiplicities. One is less than or equal to the geometric multiplicity, which is less than or equal to the algebraic multiplicity.
gm lambda is less than or equal to am lambda. Finally, the diagonalizability test provides a comprehensive criterion. An n by n matrix A is diagonalizable over F if and only if two conditions are met. 1. The characteristic polynomial of A can be fully factored into linear factors over F. 2. For each distinct eigenvalue lambda, its geometric multiplicity must equal its algebraic multiplicity. Gm lambda equals am lambda. If a matrix satisfies these conditions, then the union of the bases of all its eigenspaces will form a basis of eigenvectors for Fn, and these eigenvectors will form the columns of the matrix P that diagonalizes A. Good night. Chapter 8. Subspaces and Bases. As our peaceful journey through linear algebra continues, we now arrive at subspaces and bases. These fundamental concepts describe special geometric structures within vector spaces and provide the essential building blocks for understanding them. First, the definition of a subspace. A subset S of Rn is called a subspace of Rn if it satisfies three properties. 1. The zero vector, a column of all zeros, must be in S. 2. S must be closed under addition, meaning that for any two vectors u and v in S, their sum u plus v must also be in S. 3. S must be closed under scalar multiplication, meaning that for any vector u in S and any scalar c, the product c times u must also be in S. These three conditions ensure that a subspace behaves like a mini-vector space within a larger one. We've already encountered many examples of subspaces. The set containing only the zero vector is a subspace. The entire space Rn itself is a subspace. The span of any finite set of vectors is always a subspace. And the solution set to a homogeneous system of linear equations, also known as the null space, is always a subspace. The column space of a matrix, the range of a linear transformation, and the eigenspace of a matrix associated with an eigenvalue are all examples of subspaces. A useful subspace test can simplify the process of checking if a subset S is a subspace. S is a subspace if and only if 1. S is non-empty. 2. For all vectors u and v in S and all scalars c, the linear combination cu plus v is in S. This combined condition is sufficient because if these hold, it implies that the zero vector is in S, and that S is closed under both addition and scalar multiplication. Next, linear dependence and the notion of a basis. We want to describe subspaces in the most efficient way possible. Given a spanning set for a subspace, it often contains redundant vectors. A set of vectors v1, v2, and so on, up to vk, in Rn, is linearly dependent if there exists scalars c1, c2, and so on, up to ck, are not all zero, such that their linear combination c1v1 plus c2v2 plus, and so on, plus ckvk, equals the zero vector. This means at least one vector in the set can be written as a linear combination of the others. It is redundant. If a set of vectors is not linearly dependent, it is linearly independent. This means the only way to form the zero vector from a linear combination of these vectors is if all the scalar coefficients are zero. By convention, the empty set is considered linearly independent. The linear dependence check provides reformulations. A set of vectors is linearly dependent if and only if one of the vectors can be written as a linear combination of some of the other vectors. A set of vectors is linearly independent if and only if the only solution to their linear combination equaling the zero vector is the trivial solution where all scalars are zero. For sets with at most two vectors, checking linear dependence is straightforward. If the zero vector is in the set, it is linearly dependent. If a set contains only one vector, it is linearly dependent if and only if that vector is the zero vector. If a set contains two vectors, it is linearly dependent if and only if one vector is a scalar multiple of the other. For more than two vectors, we form a matrix where the columns are the given vectors. The set is linearly dependent if and only if the rank of this matrix is less than the number of vectors in the set. If the rank equals the number of vectors, they are linearly independent. A useful corollary states that if we have a set of k vectors in Rn, and k is greater than n, then the set is always linearly dependent.
There aren't enough dimensions to accommodate that many linearly independent vectors. Now, we move to spanning sets. Given a subspace S of Rn, our goal is to find a finite set of vectors v1, v2, and so on up to vk in S, such that S is equal to the span of these vectors. A theorem states that every subspace has a spanning set. A key question is, given a set of vectors, how do we determine if their span equals a given subspace S? If S is a plane in R3 defined by a scalar equation, we can express the plane parametrically, showing it is the span of two specific vectors. If these two vectors are not multiples of each other, they are linearly independent, and thus form a basis for the plane. For Rn itself, a set of k vectors spans Rn if and only if the rank of the matrix formed by these vectors as columns is n. This implies that to span Rn, we need at least n vectors. The concepts of spanning sets and linear independence lead directly to the definition of a basis. A set of vectors B is a basis for a subspace S if two conditions are met. 1. B is linearly independent. 2. The span of B is equal to S. B spans S. By convention, the empty set is defined as the basis for the zero subspace. A fundamental theorem states that every subspace has a basis. The standard basis for Rn consists of the vectors e1, e2, and so on up to en, where ei has a 1 in the ith position and zeros elsewhere. This set is linearly independent and spans Rn, making it the standard basis. A crucial result, that size of basis for Rn, states that if B is a basis for Rn, then B must contain exactly n vectors. This means any set with fewer than n vectors cannot span Rn, and any set with more than n vectors must be linearly dependent. If a set contains exactly n vectors, we only need to check one of the two conditions, linear independence or spanning, the other will follow automatically. This leads to the n vectors in Rn span if and only if independent proposition. A set of n vectors in Rn is linearly independent if and only if it spans Rn. This means that for n vectors in Rn, checking linear independence is equivalent to checking if they span the entire space, and either condition is sufficient to confirm they form a basis. A subspace can have infinitely many different bases, but they all share one crucial property, the same number of elements. This is captured by the dimension is well-defined theorem. If B1 and B2 are both bases for a subspace S, then they must contain the same number of vectors. The number of elements in a basis for a subspace S of Rn is called the dimension of S, denoted dim S. For example, the standard basis for Rn contains n vectors, so dim Rn is n. A line through the origin in Rn has a direction vector that forms a basis for the line, so its dimension is 1. A plane through the origin in R3 requires two linearly independent direction vectors for its basis, so its dimension is 2. These observations lead to the rank and nullity as dimensions proposition. For a matrix A, the rank of A is equal to the dimension of its column space, dim col A. The nullity of A is equal to the dimension of its null space, dim null A. These properties culminate in the rank nullity theorem. For an M by n matrix A, the number of columns n is equal to the rank of A plus the nullity of A. N equals rank A plus nullity A. This theorem beautifully connects the dimension of the column space, the dimension of the null space, and the total number of variables. Finally, we explore coordinates with respect to bases. The unique representation theorem states that for any vector x in a subspace S with basis B, there exist unique scalars C1, C2, and so on up to Ck, such that x is a linear combination of the basis vectors. These unique scalars are called the coordinates, or components, of x with respect to B. To manage the ordering of basis vectors, we introduce the concept of an ordered basis. An ordered basis for a subspace S is a basis B together with a fixed order for its vectors. This ensures a consistent representation of coordinates. The coordinate vector of x with respect to an ordered basis B, denoted x in square brackets with B, is the column vector of these unique coordinate scalars. Taking coordinates is a linear operation, meaning the coordinate vector of a linear combination is the linear combination of the coordinate vectors. A change of basis matrix. C sub b, or C in square brackets with b, transforms coordinate vectors from basis b to basis c. Its columns are the c coordinates of the vectors in b. A crucial property is that the change of basis matrix from b to c is the inverse of the change of basis matrix from c to b. These matrices allow us to easily convert coordinates from one basis to another. Good night. Chapter 9. Diagonalization. As our peaceful journey through linear algebra progresses, we now reach diagonalization, a profound concept that simplifies the study of linear operators and reveals their inherent structure. First, the matrix representation of a linear operator. In a previous chapter, we learned how to find the standard matrix of a linear transformation. For a linear operator T, which maps a vector space Rn to itself, its standard matrix, denoted T in square brackets with epsilon, is a square matrix. In this chapter, we learn how to find matrix representations of T with respect to ordered bases other than the standard basis. For a linear operator T, and an ordered basis B, for Rn, we define the B matrix of T, denoted T in square brackets with B. Its columns are the B-coordinate vectors of the images of the basis vectors under T. That is, we apply T to each basis vector in B, then find the B-coordinates of the resulting vectors, and these form the columns of T in square brackets with B. This B matrix allows us to find the B-coordinate vector of the image of any vector x, by performing matrix vector multiplication. Tx in square brackets with b equals t in square brackets with b times x in square brackets with b. There are two main reasons to use a non-standard basis. First, we might have geometrically or physically preferred vectors that naturally arise in a problem, like the direction vector of a line across which we are reflecting. Second, we might want to simplify the matrix representation itself, making it diagonal. These reasons are often interconnected. For example, for a projection transformation onto a line through the origin, we can choose a basis consisting of the line's direction vector and a vector orthogonal to it. In this basis, the B matrix of the projection becomes a diagonal matrix with entries 1, 0. Similarly, for a reflection transformation across a line through the origin, a basis of the line's direction vector and an orthogonal vector yields a diagonal B matrix with entries 1, -1. Finding a basis B that makes T in square brackets with B diagonal is not always possible, and when it is, it's rarely found by simple inspection. An important connection exists between an operator's standard matrix, T in square brackets with epsilon, and its B matrix, T in square brackets with B. These matrices are always similar. In fact, any two matrix representations of a linear operator are similar. This means they share the same characteristic polynomial, eigenvalues, determinant, and trace. Now, we arrive at the core concept, diagonalization. A linear operator T is diagonalizable over a field F if there exists an ordered basis B of Rn, such that its B matrix, T in square brackets with B, is a diagonal matrix. This links directly to eigenpairs. A non-zero vector x is an eigenvector of a linear operator T if T of x equals lambda x, for some scalar lambda, the eigenvalue. A crucial proposition states that x is an eigenvector of T with eigenvalue lambda, if and only if its coordinate vector x in square brackets with B is an eigenvector of the matrix T in square brackets with B with the same eigenvalue lambda. This means solving the eigenvalue problem for a linear operator is equivalent to solving it for its matrix representation. The eigenvector basis criterion for diagonalizability states that a linear operator T is diagonalizable over F if and only if there exists an ordered basis of Rn consisting entirely of eigenvectors of T. This means that to diagonalize T, we need to find n linearly independent eigenvectors. These eigenvectors then form the basis B. For instance, the projection transformation onto a line is diagonalizable because we found two linearly independent eigenvectors, the direction vector of the line, and a vector orthogonal to it. These eigenvectors form a basis where the projection's B matrix is diagonal with entries 1, 0. If T in square brackets with B is diagonalizable, with P inverse T in square brackets with BP, equaling a diagonal matrix D, then the entries of D are the eigenvalues of T, and the columns of P are the b-coordinate vectors of a basis of eigenvectors of T. The diagonalizability test provides a comprehensive criterion for determining if a matrix A is diagonalizable over a field F. A matrix A is diagonalizable over F if and only if its characteristic polynomial can be fully factored into linear factors over F. And, for each distinct eigenvalue lambda, its geometric multiplicity equals its algebraic multiplicity. Recall that the algebraic multiplicity of an eigenvalue lambda, am lambda, is the number of times lambda minus lambda appears as a factor in the characteristic polynomial. The geometric multiplicity of an eigenvalue lambda, gm lambda, is the dimension of its eigenspace, E sub lambda of A. The fundamental relationship is that 1 is less than or equal to gm lambda, which is less than or equal to am lambda. For diagonalization, this inequality must become an equality for all eigenvalues. If a matrix A is diagonalizable, then the union of the bases of all its eigenspaces will form a basis of eigenvectors for Rn. The matrix P that diagonalizes A will have these eigenvectors as its columns. The resulting diagonal matrix D will have the eigenvalues on its diagonal in the order corresponding to the eigenvectors in P. Our final exploration in this chapter brings us back to the powers of a matrix. If A is diagonalizable, meaning A equals PDP inverse, then computing A to the power of K becomes much simpler. A to the power of K equals PD to the power of KP inverse. Since D is a diagonal matrix, D to the power of K is easily found by raising each diagonal entry to the power of K. This provides a very efficient method for calculating high powers of diagonalizable matrices. Good night. Chapter 10. Vector spaces. As our peaceful journey through linear algebra nears its gentle close, we arrive at the expansive and foundational concept of vector spaces. This is where we generalize all the ideas we've explored from Rn and Cn to abstract sets of objects. So far, our discussions have largely taken place within Rn and Cn, or their subspaces. A common underlying fact has been that these sets are enclosed under addition and scalar multiplication, meaning that any linear combination of vectors within these spaces produces another vector within the same space. This closure property is fundamental to linear algebra. Now, we consider other sets of objects equipped with two operations, addition and scalar multiplication. These operations might be defined in familiar ways, like for vectors in Rn, or they might be entirely new. If they are new, we use special symbols, a circle with a plus sign for addition, and a circle with a dot for scalar multiplication. For example, consider the set of all real polynomials of degree 2 or less. P2R. Addition of two such polynomials yields another polynomial of degree 2 or less. Scalar multiplication of a polynomial by a real number also yields a polynomial of degree 2 or less. So P2R is closed under these operations. The formal definition of a vector space: a non-empty set of objects. V is a vector space over a field F under the operations of addition and scalar multiplication, provided it satisfies 10 specific axioms. Closure under addition for any two objects U and V in V. U plus V is also in V. Closure under scalar multiplication for any object U in V and any scalar C in F. C times U is also in V. Addition is commutative, U plus V equals V plus U. Addition is associative, U plus V grouped then plus W equals U plus V plus W grouped. Additive identity: there exists a unique zero vector in V such that for any U in V, U plus zero vector equals U. Additive inverse: for every U in V, there exists a unique negative U in V such that U plus negative U equals the zero vector. Vector addition distributive law: C times U plus V equals CU plus CV. Scalar addition distributive law: C plus D times U equals CU plus DU. Scalar multiplication is associative: C times DU equals CD times U. Multiplicative identity: 1 times U equals U, for all U in V. Any object satisfying these 10 axioms is called a vector. We've seen many examples that fit this definition. Rn over the field of real numbers and Cn over the field of complex numbers are both vector spaces. The set of all m by n matrices mmn of F over a field F with standard matrix addition and scalar multiplication also forms a vector space. Here, the zero vector is the zero matrix. The set of all linear transformations from Rn to Rm LRn-Rm also forms a vector space under defined addition and scalar multiplication for transformations. The set of all polynomials of degree at most n Pnf also forms a vector space. And the simplest vector space is the zero vector space, containing only the zero vector. These properties of vector spaces mean that many concepts we explored in Rn and Cn can be generalized. The zero vector in any vector space is unique. The additive inverse of any vector in a vector space is unique. Multiplying any vector by the scalar 0 yields the zero vector. Multiplying the zero vector by any scalar yields the zero vector. The additive inverse of a vector x is equivalent to -1 times x. The cancellation law, if c times x equals the zero vector, then either the scalar c is 0 or the vector x is the zero vector. These results, previously observed in Rn and Cn, now apply universally to any vector space. We can generalize the concepts of linear combination, span, and linear independence to general vector spaces. A linear combination of vectors v1, v2, up to vk, in a vector space V, is c1 v1 plus c2 v2 plus, and so on, plus ck vk, where the cs are scalars. The span of a set of vectors S, in a vector space V, is the set of all possible linear combinations of the elements of S. The span of any subset of a vector space is always a subspace itself. A set of vectors S is linearly independent if the only way their linear combination can equal the zero vector is if all the scalar coefficients are 0. Otherwise, it is linearly dependent. This brings us to the general definition of a basis for a vector space V. A set of vectors B is a basis for V if B is linearly independent and the span of B is V. The basis for the zero vector space is the empty set. Many vector spaces have a natural standard basis. For Pnf, the standard basis is 1, x, x squared, and so on, up to x to the power of n. So its dimension is n plus 1. For m by nf, the standard basis consists of m times n matrices, each with a 1 in one position and zeros elsewhere. So its dimension is m times n. The dimension of a vector space V is the number of elements in any basis for V. If V does not have a finite basis, it is infinite dimensional. This generalizes our intuition from Rn. The unique representation theorem also extends to general vector spaces. For any vector x in a vector space V with basis B, there exist unique scalars, its coordinates, that express x as a linear combination of the basis vectors. These unique scalars form the b-coordinate vector of x. This allows us to represent any vector as a column of numbers relative to a chosen ordered basis. Good night.